For this video, we will get into what logarithms are, how they're useful, and what applications they hold for us moving forward. So we'll get something funny like this here, and it does transform into something here. Now, you can ignore all this for now, but I want to let you know how you're supposed to read something here. This is log base b x is equal to y. So this base here is really important because if we change it to an exponent, it shifts over to become this. Okay? So let's say we have log base 3, 5 is equal to 7. Actually, let's say equal to x, sorry, because that doesn't make sense. This is the same thing if we put it into an exponent as 3 to the power of x is equal to 5. Okay. So this base to the power of whatever's on the right side of the equal sign gives you your big number inside here. I'll do one more example with you, then we'll go to the bottom. Log base 2 of, let's say we'll call it 12 is equal to a. So that's the same thing as saying 2 to the power of a is equal to 12. Let's go ahead and change what the logarithms are over here. So change from the logarithmic form to exponential form. 4 to the power of half is equal to 2. And for this one, it makes sense because anything to the power of half is the square root. And we know that the square root of 4 is indeed 2. Okay. 2 to the power of negative 3 is equal to 1 over 8. So, 1 over 8. Oops. There. Which is true because 2 to the power of negative 3 is 1 over 2 to the power of 3, which is 1 over 8. Okay. And now let's go ahead and look back on these. Okay. The first thing you want to know is the number b, I guess the letter b, right? The number it stands for at least. This has to be bigger than 0 and it cannot be 1. And then this number has to be positive. Those are the only two restrictions. Okay. B is positive and it can't be 1, and x has to be positive, and that's it. Let's move over to the next one. So, how do you change this into a logarithmic form? Log of base 3 to the power, so this is 3 to the power of 4 is equal to 81. Okay, 3 to the power of 4 is equal to 81. So log base 3 of 81 is equal to 4. Log base 3 of 1 over 9 is equal to negative 2. Determine the numerical value of the following. Log base 4 to the power of 8. We'll say this is equal to y. So 4 to the power of y is equal to 8. This over here, we make this into the same base. So instead of writing 4 and instead of writing 8, this becomes 2 squared to the power of y is equal to 2 to the power of 3. 2 to the power of 2y is equal to 2 to the power of 3. And if you took Math 910 before, you might have learned this earlier, but because the bases are the same, we can just equate the exponents. So 2 to the power of y is equal to 3, y is equal to 3 over 2. We're going to do the same thing for the next one. Log base 27 of 9, what does that equal to? Okay, we'll call this y again, or any other letter, doesn't matter. So 27 to the power of y is equal to 9. 3 cubed to the power of y is equal to 3 squared. 3 to the power of 3y is equal to 3 to the power of 2. Because of the same base, 3 to the power of y is equal to 2, and y is equal to 2 over 3. We'll skip a couple of these exercises below because that's what you'll learn for, that's what the grade 12s are learning right now. But let's look at what a logarithmic graph looks like. So, let's look at here, 2 to the power of x. We already know what that looks like because we graphed it earlier from a previous video. So let's have this one here, 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 and here. And then we have this, this, and this, and we're going to keep going. So it's a logarithmic graph that looks like this. There. All right, now that we got this, I'm going to graph this one here. Okay. So if I wanted to rewrite this as an exponential function, that's 2 to the power of y is equal to x. And I can actually start plugging in some numbers. Okay. In this instance, we don't start with our x's first. We start with our y's. So if y is equal to 0, y is equal to 1, y is equal to 2, y is equal to 3, it gives us a lot of different numbers. When y is equal to 0, x is equal to 1. When y is equal to 1, x is equal to 2. Y is equal to 2, x is 4. And when y is equal to 3, x is equal to 8. So let's go ahead and plug that in. 1, 0, 2, 1, 4, 2, and then 1, 2, 3, 4, 5, 6, 7, 8. Here. Then if we want to plug in a couple of other numbers, let's do -1, -2, and -3. Excuse me. We have, let's see, half, 1 over 4, and 1 over 8. So half, comma -1, 1 over 4, comma -2, and there we are. And if we start to connect them, here's what we get. And I'm hoping that you're starting to see that these two pictures look very similar and that there is some sort of reflection going on. And if you really want to view it like that, then, well, let me just use this. Okay, you're looking at this as a mirror. And what I didn't explain in the previous videos was that this line is actually the inverse line. So let's look at this point we had labeled over here. This was called 2, 1. If you reflect it across the inverse line, you get this, which is 1, 2. So an inverse is actually any point that's reflected along the inverse line. And what we realize is that these two equations are inverses of each other. This is an inverse function of this, whereas this is an inverse function of this. Let me do one more to really drive that point home, but I'm going to leave the line inside because I think you're starting to understand this now. And remember, if things don't make sense, just give it a quick rewatch. That's the beauty of technology here, and we are very blessed to have that. So I'll put this as red, and I'll put this as black over here. So y to the 0.5 to the power of x, we learned from before, this is y to the half to the power of x, which is y is equal to 2 to the -1 to the power of x. So y is equal to 2 to the -x. Okay. Now, using what we had before, remember that the original function looks something like this. Oops. It looks something like, sorry, it was like this. And we're going to keep going. There, it looks something like that. So a negative x means you reflect everything along the y-axis. So our new point is here, 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 and here. There, so that's the reflection there. Now, let's go ahead and graph, this one. Okay, so, let me go ahead and rewrite this here. We have half to the power of y is equal to x, which is the same thing as 2 to the negative 1 to the power of y is equal to x, or 2 to the negative y is equal to x. Plugging in some random numbers, let's go with 0, 1, 2, 3. Oh, except we'll plug it into the y for now. When y is 0, x is equal to 1. When y is 1, x is equal to half. When y is 2, x is equal to 1 over 4. When y is 3, x is 1 over 8. So let's go ahead and draw that. Let's see, 1, 0, half, and 1, 1 over 4 and 2, and 1 over 8 and 3. There. And if we go along just a couple other points, let's do negative 1, negative 2, negative 3. If we plug it in, negative 1 gives us a positive answer of 2, negative 2 is 4, and then negative 3 is 8. So 2, negative 1, 4, negative 2, and negative 3, 8, negative 3. So somewhere here. And if we notice, right, these two functions are inverses of each other because all the points are flipped across that inverse line. So this is what a logarithmic function looks like. It does take some practice, okay? But for the most part, these are the basic fundamental aspects of what you need to know for logarithms to be successful in calculus. Okay, now we're going to look at properties of logarithms and what we need to do in order to solve certain equations involving these new, systems. Okay. So log of a is equal to log 10 of a. Similar to how if I write square root 2, okay, if I don't have a number here, I automatically assume it's a 2. Over here, if I don't have any number, I automatically assume it's a 10 as the base. Log base x of a plus log base x of b. If the bases are the exact same and we are adding two different logs, we make the base the same, but we multiply the two numbers here. If we look at the third one, it's very intuitive as well. These two are the exact same bases, so if we subtract them, we take the first and the second, and we subtract the second from the first. Log base x to the power of n. Well, if we have a to the power of n inside our log function, we can just take the n and put it down here. I want to quickly note something though. If you have log 2, 4 to the 7, this is the same thing as 7 times log 2 to the 4. However, if you have log 2, 4 to the power of 7, this does not mean 7 times log 2 to the 4. You have to make sure the 7 is only attached to the 4 and not the entire log base 2 of 4. This is the thing most people make a mistake on. All we do is, if there's no brackets around the entire log excluding the exponent, then you can take the exponent down here. But see how there's a bracket here excluding that exponent? We cannot bring this to the left. You can have a rewatch there if that doesn't make any sense, and just to really fully understand that. If you have two logarithmic bases, logarithmic expressions divided by each other that have the same base, all we do is the big number in the denominator here becomes your base, and the big number in the numerator becomes whatever your logarithmic thing is. And finally, x to the log base of x of a, these two cancel out. So the answer is just a. I won't get into why that is, right, because you guys should have already learned that in grade 12. But for those that haven't taken it yet, you'll get to figure it out this year. So we can use the properties above to try to figure out what we need. Log base 10 of 4 plus log base 10 of 6 is log base 10 of 4 times 6, which is log base 10 of 24. Even though I'm saying base 10, I am not writing it, because if I don't write it, I automatically assume that it's a 10. Log base 10 of 12 minus log base 10 of 6. So log of 12 divided by 6 is log base 10 of 2. All right, here's a neat trick over here. Log base x of x is always equal to 1, given that the restrictions that we learned earlier don't ever happen. Because if we have something like, oh, log 3 of 3 is equal to y, well, 3 to the y is equal to 3. Oh, technically this is to the power of 1. So y is equal to 1. So what I'm trying to say here is, if the two numbers are the exact same and they don't break any of the logarithmic rules, this whole thing is the exact same thing as 1.